Okay, let's see how far we can get today in Notes 18. I don't know if we'll be lucky enough to finish it or not, but we'll see how far we can get, all right? And again, let me remind you that Notes 18 is the last set of notes on plane waves. And basically, this subject is being covered on the next homework 9, which I haven't put on Blackboard yet, but it'll be there later today, okay? All right.
Repeat that.
Pardon?
Repeat that.
I said homework 9 is not there yet, but I'll put it on later today. Okay. All right. Now let me just remind you of a couple things before we plow ahead here. Here's a plane wave going in an arbitrary direction called unit vector P, and the phase part of it called psi is, why is it giving me this weird thing here? Excuse me a second. Okay, and the phase function is called psi, which can be written like this in rectangular coordinates. It's convenient to introduce something called the wave vector of the plane wave, which has components in rectangular kx, ky, kz. And there's two things that's important about it that I want you to mainly remember. Number one, the magnitude of it is just k, which is k of the material, omega squared mu epsilon. And then the direction of it is this unit vector p, the direction of the power flow. So, of course, every vector's got a magnitude and a direction. That's what the k vector means, right? So you can write the phase function like this. If you like, you can write it as e to the minus j k vector dot position vector r. It means the same thing, where k vector has the components kx, ky, kz. Okay? All right, we'll take advantage of that shortly. Also remember that there's two fundamental polarizations if a wave is going in an arbitrary direction in space, what's called Tm and what's called Te. Tm means there's no hz. You can see that from the figure. Te means there's no ez, and you can see that from the figure. Okay. Fancy terminology means transverse magnetic to z, transverse electric to z. Transverse means perpendicular. So if I say transverse magnetic to z, it means the magnetic field is transverse to z, the magnetic field is perpendicular to z, and hence there is no hz. That's how you read that, okay? Now, on to the new stuff here. All right, so here's the geometry for this set of notes where we have an incident wave, a reflected wave, and a transmitted wave. Notice that the incident wave is coming from what we'll call region 1, which is often usually going to be air, but doesn't always have to be. And then the lower region, the region number 2, is some material. It could be the earth, the ocean, some plastic, who knows what it is, some material, right? Now, the incident wave, this is like the symbol for the pointing vector coming in here. The incident wave is coming in at an angle theta incident, or theta I, with respect to the z-axis, as you can see here. Theta r is the angle of the reflected wave pointing vector with respect to the z-axis. Now, it's going up, of course. And transmitted wave going down at angle theta t, transmitted angle in the lower region. Okay? Now, let me go back and point out that in the most general scenario here, see, the plane wave is going at some arbitrary direction in space, theta and phi, okay? Now, without really any loss of generality, though, we're going to assume that the incident plane wave, the incident k vector, is lying in the xz plane, or the plane of the screen. Now, so if I go back to the k vector can have x, y, z components. Okay, so if phi is 0 degrees, just visualize it. If phi is equal to 0 degrees, then the k vector stays in the xz plane like this, and we can really always rotate the coordinate system to make that so. So there's no loss of generality. We can always just rotate the coordinates to make it so. So that's what people do to keep the math simple. So the incident wave vector is in the xz plane. So there's a kx, there's a kz, but there is no ky, right? And you can always do that. So the xz plane is then called the plane of incidence, okay? It's the plane that contains the incident pointing vector here, okay? It also contains the pointing vector for the reflected wave and the transmitted wave. Again, it's called the plane of incidence, the xz plane, okay? And there's no variation of the fields in the y direction because of this coordinate system. Okay. All right. Now, our goal is to solve for what the reflected wave is and the transmitted wave. And the method of approach is to have an unknown reflection coefficient, an unknown transmission coefficient, and then apply boundary conditions at the interface, z equals 0, because there have to be boundary conditions respected. And then that allows us to solve eventually for the reflection coefficient and the transmission coefficient. So that's the overall approach. Now, I first have to take a detour and mention what boundary conditions are. Yeah, please go ahead.
The angle between the angle of transmission or the transmission x-axis.
No, notice all angles are defined with respect to the z-axis, right? That's the angle symbol there, or my attempt to make one. Okay, now boundary conditions are discussed carefully in the books, and they're also discussed in the 3318 notes. So I'm not going to do it here. I'm just going to give you what the conclusions are, and I'll invite you to read 3318 notes if you want to see the derivation. Okay, so here's the coordinate system that goes along with boundary conditions. You got region 1 and region 2. Region 1 in this figure is on top. Region 2 is on the bottom. And then unit normal points up, so it points towards region 1. All right, that's the notation for all the boundary condition equations. Now, if you want to be as general as possible, there could be a surface current flowing on the boundary. Now, that would require some kind of a sheet of aluminum foil or something there on the boundary that can support a surface current, right? Usually you don't have it, but I'm just saying to be general, it could be. And there could be a surface charge density, coulombs per square meter, sitting on the boundary too. There wouldn't be unless you put it there, like you take an electron gun and spray electrons on the surface or something, right? But if you want to be as general as possible, you can allow for it. Now, anyway, the general boundary conditions at an interface are these 4 boundary conditions right here. Now, notice this is n dot, this is n cross. When you take n dot something, you're taking the normal component. N cross a vector removes the normal component because n cross n is 0. So when you take n cross something, it's really converting it into a tangential part. It's also rotating at 90 degrees, but it's just taking the tangential part. So this says there's a jump in the normal component or vertical component of the electric flux density vector D if there's a surface charge present. This one is saying always the tangential E field parts, the part that's tangent to the boundary, always must be continuous, must match at the boundary. Normal, or vertical in this case, magnetic flux density must always be equal. And finally, this one says the change in the tangential part of the H field, it's allowed to jump, but that jump or the change in the tangential H field comes from any surface current that's flowing on the boundary. Okay, now for our purposes though, we're just going to have 2 materials present. One is going to be air usually, one's going to be something else. And there's not going to be charge density or surface current, so we don't need the most general form. So I'm just going to get rid of these things on the right-hand side, and then I just rearrange them a little bit. And then here's what I'll give you right here is the boundary conditions that we'll be using. So I highlighted in blue the first 2, because those are the ones that we're really going to be applying when we solve for the reflection and transmission coefficient. Again, this says that the horizontal or tangent to the boundary, which means horizontal here, the tangential parts of the E field must match up across the boundary. So in other words, just above the boundary in region 1 or just below the boundary in region 2, the horizontal or tangential parts of the E vector must match. That's a boundary condition. Same thing for the H field. Now, we're not going to need these, but anyway, this says that the normal component of the electric flux density must match, and the normal component of the magnetic flux density must match, as I'm stating here. But the blue ones are the ones we'll be really using, so that's why I highlighted them, okay? There'll be 2 unknowns, a reflection coefficient and a transmission coefficient, and all you need to solve 2 unknowns is 2 equations, right? So it's sufficient just to use these 2 right here. These are very convenient ones to use to solve for the reflection and transmission coefficient, okay? Now, we'll get to solving for reflection and transmission coefficient in a few minutes, but before I do that, I want to focus on these angles. Now, I assume the angle of incident, theta I, is known because somebody told you what this plane wave is coming in, striking the boundary. So somebody told you that theta I is 30 degrees or whatever. And I want to focus on trying to find what the reflected angle is and the transmitted angle. Okay. All right. And another way of saying this is I'm not worried about the polarization of the field right now. We know there's two fundamental types. One's called TM, one's called TE. And we have to treat them separately, as it turns out, because they have different reflection coefficients. But I don't care about any of that right now. No matter what the polarization of the wave is, that's not going to affect what these angles are. Okay, so I don't need to know about polarization right now. So I didn't even draw E or H. I don't care about it. I'm just focusing on the angles. Okay. Now, the incident wave vector, if I want to describe the E field of it, I can write it down like this. This is the part that's going to give me the polarization, tell me what direction it's in, but I don't care about that right now. Here's the part I really care about. This is what I call that psi function a few seconds ago. So, so it's got e to the minus j kxx. It would have e to the minus j kyy, but there is no ky, remember? And then e to the minus j kzz. Okay, and notice the x component tells me x component of the k vector. Z here subscript tells me z component of the k vector in region 1. Okay, and then the I reminds me that it's for the incident wave. In other words, this wave right here. So that's the mathematical description of the E vector for this incident wave. Now I'm going to do the same thing for the reflected E field. Notice the R stands for reflected, right? Now, notice that I have R subscript for reflected, which is logical, but I do one more thing, which hopefully is logical, but it's very important. I put a plus sign here instead of a minus sign. Now, the reason for that is that just think of like on a transmission line, the reflected wave is going backwards, right? So we'd say e to the plus j beta z, not e to the minus j beta z. I'm following that same kind of convention. So it's going up. The reflected wave, of course, is still going in the x direction. The k vector has a positive x component, but it has a negative z component. It's going up. So what I'll do is I'll say plus j kzrz. That'll keep kzr itself as a positive number. All right, so all these numbers, kxi, kzi, kxr, kzr, they're all going to be positive numbers. I already accounted for the fact that it's going up by putting a plus there. And then for the transmitted wave, it's obviously going down again, so I won't put a plus there, but I'll put a T, which stands for transmitted field. Okay? All right, now let me first consider what happens right at the boundary, which as you can see is z equals 0. If I want to consider the boundary, I'll put z equals 0, so that just makes this term go away, right? So I have these three terms here that have x variation. One has kxi, one has kxr, one has kxt. Okay. Now, what I want to claim is true is, and this is the name of it is called the phase matching condition. I'm going to claim that all the kx's are equal. Kx of the incident wave, kx of the reflected wave, kx of the transmitted wave are all equal. Now, why would that be true? So I put z equals 0 here, and then here's the fields now. So there's no y variation. So this notation means as a function of x and z, but z is equal to 0. Okay. So anyway, this is the x variation of the incident wave, the x variation of the reflected wave, and the x variation of the transmitted wave. Okay. Now you have boundary conditions that I just showed you. Okay. Now I'll go through the math of the boundary conditions in a minute, but I don't need to actually do that just to try to explain this. So boundary conditions are going to say that what goes on right here, like the total E vector, the total horizontal E vector right here, must match right here. Okay. And so that means that basically, you know, in the air region, if you want to call it that, a combination of this wave added to this wave has to be equal to this wave. Now, all three of them have different kx's. Okay. Now, I'm just going to rely on like a simple mathematical fact. If you have exponential functions, like let's just say e to the x, e to the 2x, e to the 3x. Okay, there could be a j there too. But anyway, if you have exponential functions, all with different, you know, parameters. Okay, one second. Like e to the x, e to the 2x, e to the 3x. Those are going to be what mathematicians would call linearly independent functions. Okay, I can't take e to the 3x and write it as a combination of e to the 1x and e to the 2x, right? They're linearly independent. Same thing, they put the j's there. Okay, so the only way you're going to have a hope of satisfying boundary conditions, something on one side is equal to combination on the other side, is if we have linear dependence. And what that means in turn is that all three of those kx's have to be the same. And then for all, because this has to work for all x. And then it's fair to say that one exponential can be a sum of the other exponentials if they all have the same kx. So that's not a rigorous mathematical proof, but you know that I hope you believe that. Yeah, go ahead. What's your question?
I just have my hand up, but I didn't mean to.
Oh, okay, so, okay, all right, fine, okay. All right, so that's called the phase matching condition, because, now we'll do boundary conditions in a minute, but even without going through the math, that's why the kx's have to be equal. You have no hope of satisfying the boundary conditions unless all the kx's are equal, because you just can't take one exponential and express it as some of the others unless they're all equal, okay? Mathematically, that's called the linear independence of the functions. You want them to be dependent, okay? All right, anyway, now, so if they're all three equal, then that means the first part of the equation says they're equal between incident and reflected. The second part could be said that, it could say that they have to be equal between reflected and transmitted. Now, both of those give very interesting and important results. Okay, let's take the first part of the equation. Incident and reflected kx's have to be equal. So incident and reflected wave, they have to have the same kx's. Now, here I'm writing down the mathematical expression for kx, ky, kz for the incident wave and the reflected wave. Okay, now the most general way of getting the kx, ky, and kz from a plane wave is, again, to go ahead and go back to here. If you have arbitrary, three-dimensional, vectors, a wave going in three-dimensional space, it comes from this equation right here, right? We don't need that. We're not being that general because remember, phi is equal to 0 for us when the xz plane, right? And that means, of course, also ky is equal to 0. Okay, so phi is equal to 0 in all three equations. Okay, but anyway, so it simplifies a little bit, and we have these equations right here. Now, here's, without going back to that kind of that 3D picture, though, let me suggest how to think about this. It's really pretty easy to figure out these kx and kz's once you just think about it a little bit. So let's just, I won't keep doing this, but let me walk you through it one time so you get the idea. So let's say I'm describing the incident wave. Okay, it's got a k vector. What's the magnitude of the k vector? It's in region 1, so I'm going to call it k1. Now, what is k1? Well, it's omega times the square root of mu1 epsilon 1. I don't need a value for it, but that's what it would be mathematically, right? But that's the k of region 1. Now, what direction is the k vector going in? Like this, at angle theta I with respect to vertical. So what would be the x component of this k vector? It's got magnitude k, project it horizontally to get the x component. So what am I doing? I'm taking the sine of this angle, so k1 sine theta I. What's the ky of the incident wave? Well, ky for all these is 0, right? Because all the waves are staying in the xz plane. Phi is equal to 0. Okay. So what's the kz of the incident wave? Again, magnitude k1, project it this way now onto the z-axis, so I'm taking the cosine instead of the sine. You see that? All right. What about the reflected wave? It's still in region 1, so it's still called k1, but now it's making an angle called theta r, so I'm going to call it theta r, right? But again, project it horizontally, or the k vector is going up like this. You see the arrow there? Project it horizontally, project it vertically, and now we just use theta r. Okay. Now, anyway, so these two have to be equal. Kxi is equal to kxr. These two are going to be equal. Okay? I'm not saying the z components have to be equal, of course. I'm saying the horizontal components have to be equal. That's the phase matching condition. Okay, so here we get this equation. Now, remember, it's the same k1. The incident and reflected wave stayed in the same medium, region 1. So it's the same. I can cancel it. So sine theta I is equal to sine theta r. Take the inverse sine of both sides. And we immediately have what's called, I'm sure you've seen this before in your physics class, the law of reflection. The incident angle, the incident wave and the reflected wave always make equal angles to vertical. Okay, so they're always equal, no exceptions. The law of reflection. The wave reflects off at the same angle as the incident wave, the law of reflection. Now remember, this came from setting these first two equal. We're going to get useful information by setting the last two equal also. That's what I'm going to do next. Okay, now that'll give the well-known Snell's law, which I'm sure you've probably also seen before in basic physics. Okay, but let's see how it comes from this law, the phase matching condition. Okay, so kx incident is equal to kxr, but I already did that. Now I'm going to set kx incident equal to kx transmitted and hopefully get new information here. Now I already went through this a second ago. Here's the three wave number components for the incident wave. Okay, just for practice, let's go through it one more time for the transmitted wave. Okay, because Snell's law tells us what the transmitted wave is doing. Okay, So here's this picture, this here, see the arrow there again? This is the pointing vector, which is in the direction of the K vector. So the K vector is along this line right here, making an angle theta transmitted with respect to vertical. Now, what's the magnitude of the K vector, the wave number vector in region 2? Always equal to K, right? And what is K in this region? It's called K2, not K1, because region 2 is a different material, right? K2 would be omega times the square root of mu2 epsilon 2, right? Whatever that number is, that's K2. Now, but just like I did here, if I want to get the Kx, I'm projecting this K vector going down here onto this axis right here. Of course, you could say it's taking the cosine of this angle, but that's the same thing as saying taking the sine of this angle. Okay, so sine theta t. And then finally, kzt, okay, the z component of the wave vector of the transmitted region. I want the z component, so I take this K vector going down, I project it vertically to get the z component. That's the cosine of this angle called theta t, right? So there you go. So actually, it's the same set of equations. These two boxes are the same. It's just that one has K2 instead of K1, and one has the transmitted angle instead of the incident angle. Okay, but anyway. All righty. So let's force Kxi to be equal to Kxt. Okay, so these two equations I'm circling here, right? Set them equal. Okay, so that leads to this condition here. Now, of course, I can't just immediately cancel the K's because it's not the same K like it was a second ago, right? I got K1, I got K2, and they're different. Now, one thing I can divide out from both sides if I want to, just to make it convenient, I don't have to, but it makes it convenient, I can divide out both sides by K0, the wave number of vacuum, free space, right? Okay, now when I do that, let me introduce this well-known notation. I'm sure you've seen it before. It's very common in like the optics community, but also the EM community. We define what's called the index of refraction of a material. So it could be in region 1 or region 2. The symbol N means index of refraction. The subscript I means either 1 or 2. Now, the definition of index of refraction is very simple. It's just the K of the material divided by K0. So it's a normalized K, right? Now remember, K is omega times the square mu epsilon. And again, this could be region 1 or region 2. Of course, K0 is always the same. Omega times the square mu epsilon, right? Mu 0, epsilon 0. So you can see when you divide to get the index of refraction, the omegas cancel, and then you can take the mu 0, epsilon 0 upstairs and divide these guys by it, and that converts them into relative mu, relative epsilon, right? So the index of refraction of a material simply means the square root of its epsilon r times its mu r. That's the index of refraction. Okay? All right. So anyway, if I divide both sides by K0, K1 gets converted to N1, index of refraction of the upper region, and K2 gets converted to N2, the index of refraction of the lower region. So therefore, we have this equation right here, and that is the extremely well-known, I'm sure you've seen it before, Snell's law, which can be used to calculate theta t. Remember, we assume we know theta I. In most problems, theta I is given. The materials are all known, so the index of refractions are known. So this can be used to calculate theta t, the angle of the transmitted wave. Okay. As a side note, notice that, by the way, in this note box here, let me introduce this notation. Sometimes the optics people like to say one material like region 2 is optically more dense than region 1. Now, dense doesn't mean in a mass sense here. In optics, more dense, optically dense means it's got a higher index of refraction. That's all it means, okay? And notice that I drew the lower region kind of like a darker shade. This one's like a white, it's like a gray shade. The darker the shade in my notation, the more dense it is optically, so the higher index of refraction. That's what I'm kind of thinking, right? So this could be like air going into glass or plastic or something like that. But anyway, if the lower region, number 2, is optically more dense, it's got a higher index of refraction, then this thing here, of course, is bigger than this, right? If I divide both sides, then N1 over N2 is going to be a number that's less than 1. And then when I take the inverse sign, the conclusion is always going to be that theta t is less than theta I. So when you go from a less dense region to a more dense region, this angle theta t is going to be less than theta I. Or another way of saying it, when you go from less dense to more dense, the wave bends towards the normal, towards the z-axis. This angle less than this angle. If it went from something to less dense, it would be the opposite, it would bend away from the z-axis. Okay? All right. Okay, some pretty pictures from Wikipedia. Here's an optical illusion effect because of refraction. Okay, the wave bending as it goes from one region to another. Here's an experiment that somebody did. This is an air region and some kind of plastic acrylic, I guess it's called. And somebody's shining a flashlight or some kind of beam, probably from a flashlight, onto this block. And you can see very clearly that there's a reflected wave, reflected beam. Here's the interface, right, between the air and the plastic, and a transmitted beam, right? Okay. And so if you, I didn't draw it, but if you continue the normal direction like this, then this would be the incident angle, this would be the reflected angle, and this would be the transmitted angle. And if you look at it carefully, you can see that convinced you felt that the transmitted angle is less than, for example, the incident angle. Okay. Now, by the way, just a quick side note, see, all the theory we're doing here is for plane waves, right? I mean, a plane wave is an infinite thing. It exists forever in the air region, going down, hitting an earth, fills up the infinite earth below in region 2, right? Those are plane waves. And our theory is exact for that. Now, the theory is not exact for things like beams, right? Like a laser pointer shoots out a beam, not a plane wave, right? It's focused. But you got to keep in mind, though, that even though like a laser beam might look pretty narrow, it's still very big across compared to a wavelength. Because at optical frequencies, the wavelength might be on the order of a micron or less, right? And maybe the laser beam has a diameter a couple millimeters or something. So it's still thousands of wavelengths. So because of that, even though it looks like a narrow beam to your eye, plane wave theory describes it very well when it bounces off materials. Yeah, please. Slit. But a little bit louder if you could, please.
I can't remember the experiments for. I remember it's like you're observing
Okay, you're talking about the classic double slit experiment in quantum mechanics, you mean? Yeah, the wave particle duality talking about? Yeah, no, that's nothing to do with this, except for the fact that the double slit experiment certainly illustrates that particles can have a wave-like nature, right? Because you can observe the interference pattern after they go through the slit, right? So that's what it's observing. But now here, with Maxwell's equations and EM waves, okay, technically speaking, there's a duality too, right? That's the photon point of view, right? But at microwave frequencies, we don't think that way. We just think in terms of waves, right? Okay, but at really high frequencies, especially on small scales, like with those small slits, then it's helpful to think of the duality nature, either particles or waves, right? And yeah, and that leads to interesting things, right? Is it a wave? Is it a particle? Depends on how you observe it, right? That's the duality nature. Okay, but anyway. Okay. All right, let's do a very simple example. Here's an incident wave coming from air into water. Now, there's a note down here that you may be confused because in the past, we took like distilled water, ocean water, having an epsilon R of about 81. So why am I using 1.77? Well, through microwave frequencies, water has an epsilon R of about 81 or something like that. It starts rolling off at high frequencies. Remember, I showed you that curve one day for distilled water. By the time you get to optical frequencies, people use a value that's much lower. It's about 1.77 for optical frequencies, right? Okay, so it's not the same as microwave frequencies. Okay, anyway. So when I say water has this epsilon R, I'm kind of thinking of a light wave now, like a light beam or something, not a microwave wave. Anyway, comes in from air into water. Let's go ahead and the incident angle is 45 degrees. Let's find the transmitted angle. Just a straight plug and chug example. Here's Snell's law, index of refraction. Now air has an index of refraction of 1 because mu r is 1, epsilon r is 1, square root of 1 times 1, right? And then now, and all the examples I'm doing in this notes, none of the materials are magnetic, right? So mu r is always 1. So index of fraction for us is always going to mean just square root of epsilon r, right? So just square root of this number right here. Anyway, there you go. So it's about 32.1 degrees from this equation right here. Incident angle is 45, transmitted 32.1. So indeed, it's bent towards the normal, right? As we expect. It went from less dense to more dense, so it's bent toward the normal. Now, by the way, this note here is also making a point that's kind of interesting. It says that everything works in reverse. In other words, Snell's law relates these two angles, this angle here and this angle here. Now, I usually think that this is the incident one, the wave's coming down here and it transmits into here, but Snell's law doesn't care. So everything can work in reverse. So if I call this direction the incident wave was in water coming from an angle of 32 degrees, then it would now exit like this at an angle of 45 degrees in the air, right? So you can reverse everything, it doesn't matter, okay? All right, simple, but any questions? Okay. Now, the critical angle, again, you probably saw it in physics, it's a very important angle. It's a very special value for the incident angle at which something interesting happens, okay? Now, the critical angle only makes sense when the upper region, number one, is optically denser than the lower region. You see the gray scale here, the gray shade? Darker upstairs. So that means index of refraction upstairs in region one is greater than region two. So for example, this could be a case where the upper region is water or plastic, and the lower one is air, for example, right? But the upper one is optically denser. All right, now here's Snell's law. Of course, Snell's law doesn't care which one is denser, but here's Snell's law. And here I just divided by N2, right, like this, okay? Now, the critical angle, okay, let me explain from looking at these pictures what the critical angle is. Okay, first of all, here's some typical angle, but less than what I call the critical angle. Here's the incident wave coming in. Now remember, it's going from more dense to less dense. So the transmitted wave is bent away from the z-axis, right? Away from the normal. So it comes in at some angle, and then it's bent further towards horizontal. Now, I don't have a movie, but just kind of use your imagination, okay? Imagine I'm taking the incident angle here, and I continually bend it more and more down towards horizontal. So this looks like it's 45 degrees. Maybe then I'll do 50 degrees. Then I'll maybe do 60 degrees, right? Now, as I do that, the transmitted wave is continually bent more and more out from the z-axis like this, right? Now, eventually, I'm going to get to an incident angle such that the transmitted angle is exactly horizontal, meaning the transmitted angle is 90 degrees. In other words, the transmitted wave is just skimming horizontally along the boundary. The K vector is skimming along the boundary. Now, that is the definition of critical angle. The definition of critical angle, it's still incident angle, okay? But critical angle means the special value of incident angle such that when the incident angle is that, the transmitted wave is perfectly horizontal like this. That's the definition of incident angle, critical angle, okay? So when theta I is equal to this number called theta C, theta T is 90 degrees. That's the definition of critical angle, okay? All right. Now, anyway, so with that in mind, let's just set theta T equals 90 degrees. And of course, sine of 90 is 1, right? Okay. And then when that's true, you know, when this becomes sine of 90 or 1, theta I is now being called here theta C. Okay. So now obviously we have an equation for theta C now, right? It's 1 on the left-hand side. So just take these guys across. It becomes N2 over N1, then take the inverse sine. So theta C is the inverse sine of N2 over N1. Somehow it's getting kind of cut off here, but okay. If I can see why he's, let's see, can I somehow prevent that? Let's see. Oh, okay. I'm sure what I did, but okay. Anyway. Yeah, okay. So there's a formula for the critical angle. Now, remember that critical angle only makes sense when N1 is greater than N2. So you're always taking the inverse sine of a number less than 1, right? So you can always do that on your calculator, right? It's always going to exist, right? Okay. When you're at exactly the critical angle, okay? Now remember, all kx's are equal. Kx incident is equal to kx reflected is equal to kx transmitted. And what is the kx transmitted? Just look at the picture. The magnitude is K2. It's in region 2, right? But it's now right at 90 degrees. Okay, so when you project it horizontally by taking sine, that's just going to be sine of 90, which is 1. So all the kx's just become equal to K2. Keep that in mind when I for a few minutes later when I derive some more equations. So when you're at the critical angle, all the kx's are just equal to K2. In other words, skimming horizontally. Okay, another simple plug and chug example. You're going from water, which is more dense, to air, which is less dense. Again, it's an optical frequency. So here's the epsilon r of the water. Find the critical angle. All right. So the N2 for air was just 1 again, because it's air. And then square root of epsilon r, okay, for the water. Simple math. So the critical angle comes out to about 49 degrees. Okay. So when you reach 49 degrees, that's when the picture will look like this. If the incident angle was less than 49 degrees, then the picture looks like this, right? When it's 49 degrees, it looks like this. Now, here's an interesting kind of figure that kind of, so our knowledge of the critical angle can be used to explain this one interesting effect, kind of a swimming pool effect, or here it's called the fisheye effect. So imagine, if you will, that there's like a swimming pool, for example, or it could be a lake if there's fish in it or something, but but anyway, let's say a swimming pool. So there's water here and air above it. Right? Now, let's assume I'm coming at the critical angle. Now, here, because it's a swimming pool, the water is below and the air is above, right? So it's kind of like this picture right here, except it's being reversed, right? The water is below, okay? Now, if I hit, now remember, things work both ways. We just said the critical angle is about 49 degrees. So here's the critical angle in the water region. So imagine, ignore these arrows right now, I mean the direction, just pretend it's like this. Imagine a wave is coming, going up like this from the water region, hitting the boundary, but it's at the critical angle. So what is it going to do? It's going to bend and skim along horizontally like this. So that's the critical angle effect. If the plane wave in the water was coming right at this critical angle, about 49 degrees, then when it hits this boundary, now this would be called region 2 now, right? Then it's going to go like this and bend perfectly horizontal. But now just reverse the picture. Reverse the picture. So that means a wave coming from just above the boundary, horizontal, it's going to bend and do this. Okay? If a wave is coming at less than critical angle, going out, it's going to bend and go up like this. Okay, now that's just really, you know, this picture right here upside down. Okay. Again, hitting the boundary, less than critical angle, it's going to bend like this. Again, just reverse it. So a wave coming from outside the air region at this angle here is going to bend and come like this. And by the way, Snell's law, you can easily verify from Snell's law that if a wave comes in perfectly vertical, of course, it stays perfectly vertical. In other words, if theta I is 0, theta t is 0. So this is the claim. So if you have waves coming from the air region at different angles, this is what they're going to look like. This is what's going to happen in the water region. Okay. Now, here's something that's interesting because of the critical angle effect. Just pretend that you're a fish, or maybe you're a person who's just laying at the bottom of the pool, relaxing, enjoying yourself. You know, you're looking up. What are you going to see? Okay. Look at the rays here. So notice that if you're looking up and you kind of tilt your head around, you know, looking around, you can see everything in the outside world, even these people standing, you know, on the ground here, everything by tilting your head no more than about 49 degrees. Right? So if you look straight up, you might see planes overhead. If you look up at this angle, you'll see maybe a tree over here. If you look up at the critical angle, you're going to see a person standing way over here on the shore. All right. What do you think? What do you think you're going to see if you tilt your head more than 49 degrees and you look this way? What do you think you're going to see? Just the water? Okay, yeah. In fact, we'll talk about in just a second what happens when the wave is incident beyond the critical angle. That's really what this is, beyond the critical angle. But it turns out that all the power gets reflected. So a wave coming in like this is actually going to do this. So if you look beyond 49 degrees, you're going to see just a reflection from the bottom of the pool. Right? Okay. Next time it's warm and you're in the swimming pool, you can verify this. Okay. All right. Here's at the critical angle one more time, verifying one more interesting thing. Remember, all the kx's are equal to k2. Now, let me remind you, this has become very useful. Remember, we have this thing called the wave number equation. In any region, it has to be true that kx squared plus ky squared plus kz squared is equal to k squared. And there's no ky in it for us, right? So kx squared plus ky squared is equal to k squared. Kx squared plus kz squared is equal to k squared. It's valid for region 1, valid for region 2. Now, if I'm in region 2, okay, so if kx squared plus kz squared is equal to k squared, and k squared is now k2 squared, then just solve for kz, right? Kz must be the square root of k squared minus kx squared. So that's where this came from, okay? But if you're at the critical angle, then kx of the transmitted wave is what we call k2. Oh, that's interesting. So we get square root of k2 squared minus k2 squared or 0. So right at the critical angle, there's no vertical variation of the fields. Remember, vertically in region 2, what does the z variation look like? E to the minus j k z t z, right? So if KZT is 0, there's just no variation in the fields. Kind of interesting. Now, here's the most interesting thing, though. You're now beyond the critical angle. So maybe, so if this is like water and air, maybe the critical angle was at 49 degrees, and now you're at, let's say, 60 degrees, or wherever this picture is. So now you're beyond the critical angle. What's going to happen? This is where life gets interesting. Okay, so theta I is beyond theta C. Now, that means the kx of the incident wave. See, the kx, see, right at the critical angle, kx would be equal to k2, right? But now you're making the incident wave even further down towards horizontal, which is going to increase the kx. So kx is now greater than k2. Okay, if you want to see it mathematically, here it is. Okay, kxi is equal to this equation here. Okay, but it's greater than this because theta I was greater than theta c. Okay, but then k1 sine theta c by Snell's law is k2 sine 90 because you're at the critical angle. Sine 90 is 1, so you get k2. Okay, that's the math if you want to see it. But anyway, but the conclusion is when you're beyond the critical angle, kx, the incident wave, is greater than k2. At the critical angle, they're equal. Beyond the critical angle, kx, the incident wave, is greater than k2. Now keep that in mind. Now here's that same equation for kz of the transmitted wave. Again, the wave goes as, here it is, e to the minus j kz tz. Now, of course, it also has this x variation, but I don't care about that right now. The z variation is what's important here, e to the minus j kz tz. Okay, so bear with me as I go through this math here. So here's the formula from that wave number equation. Now, here's the steps. Kx of the transmitted wave is the same as kx of the incident wave because all three, incident, reflected, transmitted, are equal. Next step. Notice that I reverse the order inside the square root. It's like factoring out a -1, so square root of -1, which could be called j or minus j, but I'm going to call it minus j. That's the correct choice, as you'll see in a second, because the wave has to be decaying as it goes down, not increasing. That's non-physical. You'll see that more clearly in a second. So that's why the square root of -1 is being called negative j, not plus j. So anyway, and so you can see here, in fact, kxi is greater than k2. So when I write it like this, see, I'm taking the square root of a positive number, and I'm going to, principal square root, radical sign, I'm going to call that a positive number. So you can see it right here before I go any further. Kxt is negative j times a positive number. That's the correct choice. Just like a wave on a lossy transmission line is decaying or something like that. You know, it's got to decay, can't be increasing. Minus j, not plus j. Anyway, so the kx of the incident wave is, you know, k1 sine theta I, we saw a minute ago. Okay, let's factor out a k0 squared and call it k0, and that converts the k squared to index of refraction squared. Okay, that's about as far as you can go, I guess, except let me now just introduce terminology. So this term in front of the minus j, called k0 times the square root, I'm going to call it alpha, kind of familiar notation. Alpha is an attenuation constant, right? That's why I want to call it alpha. Same terminology you had like on transmission lines. So it's called alpha zt. Alpha in the z direction going along with k in the z direction, the component z, you know, kz. T means transmitted wave. So notice that when I take this equation for how, this is called the psi function, the phase function, telling me how the wave varies with x and z. Again, I'm not worried about the polarization or anything, you know, but this is how it varies with x and z. And again, I don't care about the x variation so much. Just look at the z part. If I use this notation right here and plug in for here, so this gets plugged in right into here. Minus j times minus j is -1. So here's the important thing. When you're beyond the critical angle, the wave is decaying exponentially as you go down into this region 2. There's an attenuation constant, and there's the formula for it. Now, if you tell me what these, if you tell me the incident angle, if you tell me materials, if you tell me the frequency, I can actually calculate a number, right? But this is just a formula. Now, this is very interesting. This is kind of the first time we've seen this. We'll see it again when we talk about rectangular waveguides, but this is an interesting effect. We have an exponential decay, an attenuation constant of this wave, but there's no loss here. Okay, I mean, there could be, but right now I'm assuming that all these materials are lossless, like water just has a real epsilon r, right? 1.77 or whatever. So these materials have no loss. So why in the heck would a wave be attenuating exponentially if there's no loss? Now that never happens on a transmission line, right? On a transmission line, the alpha comes from what we call R and G, right? Loss gives you alpha on a transmission line. This is a totally different physical effect here. This is what people call evanescence. Evanescence is a fancy word for meaning that the wave is decaying exponentially, even though there's no loss. So it's a very different type of effect. So that can happen with a wave. It's not due to loss. It's due to the fact that you're beyond the critical angle, and that's enough to make this wave decay exponentially. So the wave is the amplitude is decaying exponentially. Now, but you can of course convert this as dB per meter if you want to, right? 8.686. But anyway, but it's not a loss effect. Okay. Now, I think I explained it here. Okay. Well, yeah. So here, now here's a picture of what's going on in terms of the power flow if you're beyond the critical angle. One thing that's interesting is that in this upper region, the incident wave is a pointing vector as these arrows show coming in like this. The reflected wave is a pointing vector going out like this. But now, what is the direction of the power flow in region 2 if you're beyond the critical angle? It's kind of an interesting question. Now, let's see, if you're not beyond the critical angle, if you're like this picture right here, then it's pretty obvious. This right here, theta t, is the angle of the pointing vector, the angle of the k vector. That's the way power is flowing, right? But remember, you get to the critical angle, it looks like this, and then you keep on going, you cannot even calculate a theta t anymore, right? I mean, because now you're beyond the critical angle, so what's going to happen? Now, so it's kind of hard to justify this without doing the math and actually calculating the pointing vector, but here's the answer. So when you're in region 2 and you're beyond the critical angle up here, the pointing vector in region 2 becomes perfectly horizontal, has no z component to it. Now, when you're beyond the critical angle, sometimes people get confused on this. When you're beyond the critical angle, it doesn't mean that there's no fields in region 2. There are. And because there's E and H fields in region 2, there's a pointing vector in region 2, but it's flowing perfectly horizontal, which you can do by actually calculating E and H, we have E cross H conjugate. Now, if you see the size of the arrows is supposed to be the magnitude of the pointing vector. You see, not only is it horizontal, but it's getting weaker and weaker as you go down. That's because of the alpha, the attenuation constant, right? The fields are decaying exponentially, and therefore the pointing vector is 2. Of course, the pointing vector is like e to the minus 2 alpha z, right? Okay, but the pointing vector is decaying exponentially as you go down, but it's flowing horizontally, okay? Now, also another interesting thing that I'm saying here is, when you have a picture like this, some power has got reflected, some power has gotten transmitted, and that means it's actually crossed from the upper region down to the lower regions, crossed the boundary. Power has crossed the boundary, right? Now, when you're beyond the critical angle, no power actually crosses the boundary, okay? It can't, because that would actually violate conservation of energy, right? Okay, without elaborating too much on the math, let me just give you a quick and dirty explanation. Let's assume that there was a normal component of the pointing vector, just assume it. That means so much, there would be watts per square meter crossing the boundary going from region 1 to region 2. How could that be? So just imagine a little kind of like a little tube or something, a little cylinder, and you got vertical power flowing in that tube, and of course, crossing the boundary. Now, conservation of energy would say that whatever watts per square meter crosses that boundary in that little tube, it has to either get absorbed or it has to flow out at the bottom of the tube. But this is a lossless region. Nothing's getting absorbed. And the fields are decaying exponentially, so nothing can be flowing out of that little tube. So if you have a pointing vector watts per square meter crossing vertically inside this little tube, where's it going? It's not being absorbed. It's not leaving at infinity. Where's it going? That's a contradiction. So conservation of energy forces the conclusion that there can't be any vertical power flowing here crossing the boundary. Okay, so at the boundary, there's no vertical component of the pointing vector. It's perfectly horizontal, and that ends up staying true in the whole region. Pointing vector is perfectly horizontal. There are fields, there is a pointing vector, but it's horizontal and it's getting weaker and weaker as you go down. That's what the picture looks like. Okay. Okay, this is some interesting stuff that's almost like a total digression, but if you ever hear the word metamaterial, it's a hot area of research in the EM community and also the optics community. A metamaterial is an artificial material. That's what meta means, beyond, from the Greek meta. Metamaterial is an artificial material that has properties you cannot find in nature, including index of refraction. Okay, so like, for example, we just talked about Snell's law. A normal material would have a wave coming in, And if it's a denser material, region number 2 is going to bend like this, right? That's the normal Snell's law. What if you had a crazy material that had a negative epsilon or a negative mu r? Weird things can happen. Like the wave comes in from this direction, and instead of bending like this, it has a negative angle, bends like that. Some people call that a left-handed metamaterial. Don't worry about why that is. But anyway, weird things can happen when you have negative epsilon and mu. You're not going to find it in nature usually, but you can make materials, usually periodic materials like this, that can do it. It's kind of weird. Okay, here's Wikipedia article. We're going to read more about it. Here's one application that still sometimes people are doing at conferences. They're trying to come up with metamaterials that have exotic materials, exotic properties, epsilon and mu, that are not found in nature, that can allow these waves, as they refract and bend through the material, to do interesting things, right? Not the normal Snell's law, but bend in weird ways. And one application could be what's called cloaking. So, for example, here's an ideal three-dimensional cloak. Imagine that here's some material, some object that you want to quote cloak, render it invisible. So imagine that this region, the spherical region here, has some kind of epsilon r and mu r that are varying throughout the region in just the right way, including possibly being negative. Okay, then you can design it so the waves do something weird like this. All the waves come in, they bend around the object, and then they exit like this. So now picture you're an observer. Your eye is right here looking this way. Are you going to see this object? No. You're going to see what's over here. Even though this thing is sitting right in front of you, you don't see it. It's cloaked, right? And here's a very simple primitive 2D cloak that this is coming from one of the early inventors of the metamaterials, Professor David Smith. But anyway, so here's a 2-dimensional version. People are still working, to be honest, on 3-dimensional versions because that's a lot harder to achieve than 2-dimensional versions. You'd love to cloak an entire, battleship or tank or something like that, but that's a lot harder to do, right? But here's a primitive experiment using this 2-dimensional cloak where you can see it works. Here's a plane wave coming in, and then exiting here is an undisturbed, perfect plane wave. This plane wave exiting is exactly the same as this plane wave entering. It's as if this thing wasn't even, as if this whole region here didn't even exist. So this is the cloak, okay? But so here's the inside of the cloak. I could put anything I want there. A metal object, a cell phone, who knows what. I could put anything I want in this green region right here, and this plane wave doesn't see it. Just goes straight through. It's kind of neat, isn't it? So anyway, probably said too much. But anyway, weird things can happen if you allow epsilon r and mu r to be negative and to vary in ways that wouldn't be predicted, that don't happen in nature. And it's a hot area of research called metamaterials. Again, go ahead and Google it if you want to see more about it, all right? Anyway. Okay, so now we're up to the next and final kind of important topic here, and that is how do these plane waves reflect and transmit? Okay, we know about the angles now, law of reflection, Snell's law, but how do they bounce off? There's a reflection coefficient, there's a transmission coefficient. Now, let me remind you, now it's really important to consider the polarization of the wave because TE and TM are going to have different reflection coefficient formulas and transmission coefficient formulas. Now, here is a TEZ wave, transverse electric to Z. It means there's no EZ. Another way of saying TEZ, and in fact, this is what a lot of textbooks will do. They'll say, this is a wave polarized perpendicular to the plane of incidence. Now, let's go over both to make sure you understand both. what happened? Why did it do that? Never did it before.
There's a warning at the top left.
Oh, there was a warning
Yeah.
on the screen here? What did it say?
Temperature.
Oh, okay. Well, yeah, I can see something like a flashing red light too on the front of it. Let's just wait a minute. That's weird. Huh. Okay, I think it's going back to, oh, okay. Well, that was weird. Okay. Or anyway, as I was saying, I'm sorry, if you don't mind, I'm trying to getting you this. I just better late than ever. As I was saying, even though it's probably clear already, let me go over one more time the notation so you understand. TEZ, that means there's no EZ. Look at this wave, EH. Look at Z direction, there's no EZ. Now, if you visualize, so E is in the Y direction coming out of the screen, H is in this direction, see E is perpendicular H. And if you visualize taking E cross H, the pointing vector is going to be going this way. Hopefully that's all clear. That's what a TEZ wave would look like for the E and the H fields. Okay, now the E is in what we call the Y direction. The plane of incidence, remember, is XZ, the plane of the screen. Y is, of course, perpendicular. So remember, polarization of a wave is based on the direction of the E field, not the H field, right? So we would say the E is perpendicular to the plane of incidence. So indeed, the wave is polarized perpendicular to the plane of incidence. So that means the same thing as TEZ. E has no Z component. Yeah, the H vector does, but not the E. Hope that notation is clear. Now, anyway, we have an unknown reflection coefficient and unknown transmission coefficient. I label E and H for all three of the waves. Okay. All right. Now, here is the mathematical form of the incident E field, the reflected E field, and the transmitted E field. Notice that I have an arbitrary amplitude coming in called E0. All the waves have E in the Y direction, but I allowed for a reflection coefficient and a transmission coefficient. Okay. Yeah.
What is the reflection coefficient? Like the symbol's name?
What's sorry?
What is the gamma?
So I'm using the similar notation we did for transmission lines. Remember in transmission lines, gamma is reflection coefficient, right? And capital T was transmission coefficient, right? So it's a logical notation. Do it for plane waves too. Okay. All right. Now here's a formula for all the components, and we've already seen that before. Okay, fine. Now, so there's two unknowns. Gamma T. I need two equations. I'm going to get it by saying that horizontal or tangential E has to match across the boundary. Horizontal or tangential H has to match across the boundary. So quickly, here's tangential E, horizontal E, which now for us means EY, right? Just above the boundary, total EY would be incident plus reflected, just like on a transmission line. Just before the junction, total voltage would be incident plus reflected, right? Across the junction, total, there's only one wave going down, so total is just transmitted. So take these equations and just plug in incident plus reflected is transmitted. Now, let me just quickly go through the math. This is a boundary condition. This has to be true at the boundary. So I said z equals 0, so get rid of those Z terms. Okay, all the KX's are equal. That's a phase matching condition. So all those exponentials are equal, get rid of them. All the E0 term is just a common constant, get rid of it. So it reduces down to simply nothing but this. Well, that looks familiar, doesn't it? 1 plus gamma is equal to T. Where have we seen that before? All right? Transmission line theory, right? Exactly the same reason. You know, that was called the Kirchhoff law, right? Incident plus reflected voltage has to be total voltage. Okay, now it's called the boundary condition. Incident plus reflected E field has to be total E field, but same principle. Okay. All right. Now, quickly for the magnetic field. I'll get that from Maxwell's equations. So here's Faraday's law. Use it to get the H field. I'm not going to bore you plugging all that in. You can do that at home if you want. But if you calculate that for all three waves, I've added it here. The H incident, H reflected, H transmitted. Okay. Now, and we enforce the boundary condition for H. Just above the interface, total H, incident plus reflected, must be just below the interface, total. Right? This time I even gave you less algebra, but it's the same kind of thing, right? So in the H, remember the H has both X and Z components. Okay, but I'm taking the X. So what I'm doing is I'm looking at this guy here, and this guy here, right? The X. The boundary condition doesn't say total H has to be matched across the boundary. It says horizontal or tangential component. That's X here, okay? So anyway, do the same kind of thing, set equal to 0, phase matching condition, cancel out those terms. So it ends up with this condition now. Okay, I'm maintaining the color code here. I don't know if you like that or not, but incident, reflected, transmitted, different colors. Okay, anyway. So you got these two equations, and I'm not going to bore you with the algebra to solve them either. It's very similar to solving for the reflection coefficient of transmission line, where again, you have unknown reflection coefficient, unknown transmission coefficient, And now the two equations would be Kirchhoff voltage law, Kirchhoff current law, instead of two boundary conditions. Anyway, you go through the math. Here's the answer for the reflection coefficient. And again, transmission coefficient is 1 plus it. Now, it looks it looks pretty complicated. But now, for the grand finale, let me give you a really nifty way to remember this. Okay? And you see a term omega mu over kz. Of course, they all have this, in both regions, it's the same omega. If you're in region 2, it's called mu2, permeability of region 2. In region 1, mu1. Now, if you're in region 2, kz is called kz transmitted. It could also be called kz2 if you want, but we call it kz transmitted. If you're in region 1, it's called kz incident. You can also call it kz1 if you want, but kz incident. Okay, so the general formula that holds for either region 1 or region 2 is omega mu over kz of that region, that mu, that kz of that region. Now, if you think that way, then look at what this simplifies to. The formula for reflection coefficient is Z2 minus Z1 over Z2 plus Z1, where Z2 is just a simple formula, omega mu over kz, either for region 1, where kz1 is also called kzi, and region 2, where kzt could also be called kz2 if you want. Now, what the heck does that remind us of? This is exactly the formulas for gamma and t when you have a transmission line and a wave is coming incident. It's got a reflection coefficient and a transmission coefficient. So that's the most beautiful, elegant way to pass the final answer and to remember it. The reflection and transmission of a plane wave works 100% identical to what we already know for a transmission line. The only thing new that you got to remember, really, is that what would be called normally the characteristic impedance of a transmission line becomes this formula for a plane wave, a TE plane wave, omega mu over kz. It's playing the role of characteristic impedance. We don't call it that, but it's playing the same role. If you remember it that way, this is all simple. Really, really simple. Okay? Now, how much time? I'm going to have to put in a few minutes. Now, let me not bore you with all the math, the TM case. I hope that's okay. If I let you read at home the TM case, because I went through all the math for the TE case, I'm just going to say it's similar, right? But in the TM case, I'll write, here's the polarization. H is in the y direction. Okay, E stays in the XZ plane. So this is called polarized parallel to the plane of incidence, but also be called TM because now H has no Z component. I'm going to describe incident H, reflected H, transmitted H. Now, why did I put negative gamma instead of plus gamma? Because I want to still base reflection coefficient on what the E field is doing, not the H. And we'll see plus gamma comes out in the E field reflected. There's a note to that effect here. Unfortunately, Shannon-Collins book doesn't do it that way, but anyway. So anyway, I know I'm going quick, but I just want to summarize the result. Here's the E and H for all three waves in the TM case. Okay, apply boundary conditions. You get similar looking equations. You still have 1 plus gamma is T, but now this one looks a little bit different. You solve the math, and it comes out looking exactly like the transmission line problem again. Okay, here's the thing that's different. In the TM case, you get a different formula for these, quote, characteristic impedances. Oops, careful. So it's not omega mu over kz. It's kz over omega epsilon. So let me quit here. Here's a summary of both cases, the grand finale. So now we're ready to work examples, but we'll do that next week. Okay, but here's the grand finale. So when you have a wave coming in, reflecting off and transmitting, just think of it as a transmission line problem. And what would be the characteristic impedances are given by these formulas here. Now, M just means it could be 1 or 2, region 1 or region 2, upper or lower. But TE is omega mu over kz. TM is kz over omega epsilon. Here's elaboration of those formulas for the kz's that we've seen collected together. So now you can do any reflection transmission problem. And that's what we're going to do in examples, and even power. Remember, power reflected is magnitude of gamma squared, just like for transmission lines. So if I say how much percent power is reflected, how much percent power is transmitted, no problem. But that's what we're going to do next week on examples, okay? So for reading ahead, please pick up somewhere right around here about page 35 and finish reading this. We'll finish it on Tuesday, and then I'll put the next set of notes on Blackboard for you too as well, okay? All right, thank you.
Yeah.